Hey folks, it's Mr. Robeson here still. We are looking at the last one in 9.6, 9.6 part C. So we're still looking at to use geometric sums to make power series. This time we're going to use derivatives and integrals as well. Should be fun. All right, so we already looked at this once before. So we already said that if we can write f as some sort of a power series, that we can take the derivative of f, and we just bring down the n and so on, and we can take the integral of f, and which means we integrate and add that plus c out in front. All right, so we remember that is a thing we can do. We might have to find some c's here. We've also said that the radius stays the same. The interval is basically the same interval. We just have to check the endpoint behavior because the endpoint behavior can change when we integrate and take derivatives. All right. So sometimes, though, it's much easier to find a power series for a function's derivative or for a function's integral than it is for the actual function. So sometimes we'll do the power series for like f prime, and then we'll take the integral of it to move back up to f. Or we can take the integral of the function and find its power series, and then take its derivative to go back to f. So it's kind of a neat little trick. All right, so here's one we want. The power series for f of x equals ln of x centered at 1. So we could just take a bunch of derivatives here and then plug in 1 over and over and over again and then look for a pattern, and that would get us a power series, actually a Taylor series centered at 1. That would work. But there's an easier way to do it. If you recognize that the derivative of ln of x is 1 over x. And we've already done this power series. We did this earlier in the presentation in 9.6 part A. We can rewrite this as 1, or so plus 1 minus 1 plus x, like that. And then we can factor out a negative from the bottom. 1 minus, and that would be 1 minus x, like that. And now we can write that as a series, 0 to infinity, of, no, a is 1, that's our r, to the n, like that. All right, now usually we move it around a little bit. We usually don't write 1 minus x, we usually write x minus 1. So we can pull out the negative 1 from this guy and say this is negative 1 times x minus 1, like that. So it would be the sum from 0 to infinity of negative 1 to the n, x minus 1 to the n. And this converges for x minus 1, an absolute value less than 1. So negative 1 is less than x minus 1 is less than 1. Add 1 to each side. 0 is less than x is less than 2, which makes sense because we're centered at 1. All right, so this is the derivative, though. That's our derivative. And we want to go back to f. So if we integrate this with respect to x, that'll bring us back to our function. So if we take the integral of this guy, we get c plus the sum from 0 to infinity of negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. All right, now if we just plug in 1, we should get 0. So this is ln of x is what that's equal to. If we plug in 1, we get 0. If we plug in 1 here, all those terms are going to be 0. So that means c is going to have to be 0. All right, just by plugging in 1 everywhere. All right, so we get that ln of x is equal to the sum from 0 to infinity of negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. So we could just say, well, starting at 1, that would also work. And this holds for 0 is less than x is less than 2. Right, that's where it converges. So any number between above 0 and less than 2, we can plug into this, and that would give us an approximation for ln of x. All right, let's try another one. G of x is arctan, and we want that centered at 0. How the heck do I do arctan? I mean, we can take derivatives of arctan. The derivative of arctan is, gosh, what is it? It's 1 over 1 plus x squared, right? Well, wait a minute. That's not so bad. That's pretty close to what we want. We just want a minus here. Like that. So now we can say this is the sum from 0 to infinity of negative x squared to the n. Or the sum from 0 to infinity of negative 1 to the n, x to the 2n, right? 2 times n, 2n. And I bring in the n to this negative 1 there, and there we go. All right, but that's the derivative. So that means we need to go up a function. We need to take an integral with respect to x. So if we integrate that with respect to x, we get that g of x is some constant plus the sum from 0 to infinity of, well, it doesn't affect negative 1 to the n. X is now going to be to the 2n plus 1 over that new exponent, 2n plus 1. All right, and that's arctan. So that should be arctan of x. Centered at 0, arctan of 0 is 0. So we get 0 equals c plus all this stuff. But if we plug in 0 here, it's going to be 0 for all of those. So that means our c also equals 0. So we get that arctangent of x equals the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Now we're not sure what values this converges for, but if we go back up to here, or to this one here, we'd say the absolute value of x squared needs to be less than 1. All right, so that basically means x is going to be between 1 and negative 1. All right, so we can try both of those endpoints in here and figure out which ones converge and which ones diverge. If we plug in 1, we still got this negative 1 to the n over 2 to the n. It's an alternating series, and that will converge for 1. So 1 is good. If we plug in negative 1, what's going to happen here? Looks like those negatives are probably going to cancel each other out. So, no, this one's always going to be odd. So this one would be negative 1 every time. So it's also going to converge because it's still an alternating series. All right, so it works for both endpoints if I plug in negative 1 or positive 1 in there. So that means arctangent of x will converge on that interval. Cool. All right, so that's how we can get power series using derivatives and integrals. So we can take derivatives of functions or integrate functions and try and make them match one of the forms we want, that geometric series form.